really have a ton of stuff to present on the board, but hopefully everybody knows that we have an exam coming up, right? Exam on Monday. How are people feeling? Thumbs up, thumbs down, so. Seeing a couple different options. So we should be studying those. If you have any questions over the weekend, I'll try to check my email. Feel free to email me. And I'll also make sure to open up those weekly quizzes we've been doing so that you can go through those and check your answers now that everybody should have completed them. So you'll also have those to study from. Separately, I have a question about SI for this week. Did people go to SI? Okay. I got an email, not specifically about you guys, don't worry. I got an email that there was some confusion between different classes about the electrochemical driving force. Who is still like confused about that, or who was talking to the other classes and became more confused? Okay, cool. So I'm going to show you and make sure that you know how everybody else is, I think, doing it. As I mentioned when we did it before, I find this way to be more difficult and more confusing, but everybody's brain is different, so maybe this will be more helpful for you guys. And after we talk and go over any questions or things you want to review, I have a worksheet. I just sent out an announcement on Brightspace, so we'll have some structured stuff to go through, because I find actually going through questions can kind of prod your mind about what you're confused about. So, where is, I'm not having an annotation tab. Sorry guys, I guess I forget how to use Brightspace today. Sorry, Zoom. That's very Friday. Okay. So the way I was teaching you to think about the electrochemical diffusion or driving force was just to think about that equilibrium potential and realize that the ions are just going to move in whatever direction gets our charge inside the cell to that equilibrium potential. But the other groups have been going through a flow chart. And obviously I'm going to argue to you why my way is better, which is that the flow chart does kind of require you to have information about the chemical driving force, which you won't always have, which is why I find this a little less useful. So let's say you do have information about that. So if we're determining the electrochemical driving force, the first thing we want to do, if we are able, so you want to identify the directions of the chemical driving force and the electrical driving force. So since we're reviewing, how would we identify the direction of the chemical driving force? What would you be looking at? Concentration. So we'd be moving from an area of what concentration to an area of what concentration? High to low. High to low, yeah. So when we're paying attention to that concentration gradient, just a reminder, we're looking at the concentration gradient of that specific molecule, that specific ion. Whereas when we talk about the electrical driving force, that's all the ions that are affecting charges in the environment. So that's the difference between CDF and EDF. Okay, so how do we tell which direction our electrical driving force is pointing? How do we tell the EDF? Differences are attractive and like things want to be apart. Right, so positive and negative are going to go towards each other, but if we have a positive and a positive, they're going to go against each other. Okay, so say we have our cell. Let's say, I'm going to write it in here, that negative 70 VM. And we're thinking about a sodium ion. So we would need for this step information about the CDF and the EDF. So I'm going to draw in some sodium ions. So in this situation, if those little red dots are sodium ions, which direction is the CDF for sodium, in or out? Yeah, so we'd have a CDF in. And what about the EDF? That positive charge on sodium is attracted to that negative membrane potential, that -70. Okay, so we're pointing in the direction, the same direction, I should say. So that this brings us to our first split in this chart. So now that we've identified these, we're going to split. So one thing we might have happen, right? Our CDF and EDF might be in the same direction. If they're in the same direction, which way would our electrochemical driving force point then? It goes the same direction because we're only going one direction, CDF and EDF. So in that case, that we've drawn up here, which direction is our ECDF? Yep. Okay. So then we have then we have a more difficult situation if they go opposite directions, right? So this is where we're going to have to figure out whether we're following the chemical driving force or the electrical driving force. So what do we flip here? I'm going to grab my eraser. I'm going to erase. Let's do our chemical driving force.
Membrane potential was at like positive 70, then like the sodium would move out opposite.
So if it was at positive 70, the direction of our electrical driving force would flip. Yeah. So yeah, and we can draw that example instead. Let's see if I'll redo this. Yeah. So let's put that chemical driving force back on, and instead we'll flip the membrane potential. That's a good idea. So now we're going to make our membrane potential positive 70. So this flips our EDF. Does everybody see why that would be the case? Why that would flip the EDF? Okay, yeah. So it flips the EDF because now that positive is repelling the positive on the sodium. Flipping it. Okay, so now we have this situation where we know that the chemical driving force and the electrical driving force are in opposite directions. So at this point, without any more information, we don't know which direction the electrochemical driving force would point because all we know is the direction. We don't know the magnitude of these forces, the CDF or the EDF. So this is where we pull in our equilibrium potential to help us figure out what's going to happen. So we're going to logically have three situations, each of which is going to give us a different outcome. Okay. So when we compare, I should have, one more, right? So opposite directions, we're going to compare sizes of the equilibrium potential. So in this case, it would be ENA because we're talking about sodium, but we're writing X because we could do this for any ion. Okay, and the membrane potential, VN. So that's what we're doing. So from this point, we could have a situation. We'll do the middle one, because that's the simplest. Okay, so our first situation would be where the two are equal, right? So EX equals VM. So in this case, at the top, let's just say I told you that ENA, the equilibrium potential for sodium, let's say it was positive 70. What would happen then? Which direction would the ECDF point? Which direction would sodium ions move? Yeah, exactly. So when we are at the equilibrium potential, and that is our membrane potential, when these two are the same, that is basically the definition of the equilibrium potential. So that means our two forces are equal and opposing, our chemical driving force and electrical driving force. So we're going to say then our electrochemical driving force, they're equal and opposing the EDF and the CDF, so it would equal 0, which would mean ions at equilibrium, no net movement. So that's going to leave us our other two situations. So let's say we have a situation where our equilibrium potential is bigger, stronger than our membrane potential. Okay. Oops. Sorry, that should say if, not F. Oh boy. Okay, so for sake of argument, we'd have to redraw this whole thing. Okay, so I'm just going to tell you. So if we're in a situation where our equilibrium potential is greater than our membrane potential, this is going to mean that our CDF is bigger than our EDF. And when our CDF is bigger than our EDF, what happens? Yeah, so our CDF is bigger than our EDF, which we would know because our equilibrium potential is greater than our membrane potential. That means that the ECDF will go along with the CDF. So what's our final comparison going to be then? What do you think we're comparing over here? Yep. And then we can compare. Do it either way, right? So if our VM is bigger, what would that mean in terms of the relative sizes of the CDF and EDF? Yep. I mean, our EDF is bigger. So which way would our EDF flip or ECDF go? Yeah. Then go whatever the direction the EDF goes.
How do you find that?
The equilibrium potential would be given to you. No, it's something that would be like experimentally determined. So it kind of tells you someone else has done the math and the research to figure out like what the concentrations are and what the magnitude of the EDF is.
Did they ever show you?
And like it depends on temperature as well.
Did they ever like put it on the picture?
So they might like write, right, E and A equals, actually, the actual true value for most of our cells is 60. And this just happens to be true, and it'll be helpful to remember that because we'll have to remember that in unit 2, because this is really important for our neurons. So it would just say it like that. There isn't like a drawing that would tell you what that number is. It would just be a label. If you didn't write this flow chart, go ahead and take a picture just so you can practice using this, see if it makes more sense to you, if this helps you.
What exactly does the equilibrium potential mean?
The equilibrium potential means that these two things are equal, which also means that there's no net movement because we add together those two things to get our ECDF. So the fact that they are equal means that the electrochemical driving force is 0. And when the electrochemical driving force is 0, that means we won't have net movement. There's nothing pushing it. Yeah.
You say they're equal, you're talking about the rate, both of them are equal, right? Or like the force, like the driving force is equal between the two. There's like no like number value for CDI.
Right. Yeah, and we just won't see number values for what those are. You'll basically only see sizes of arrows. But yeah, when we say they're equal, we're talking about the force. Right. I don't even know what units we measure that in when we measure the CDF. I don't know how small exactly they are. But yeah, it's a measurement of the force. So not really the rate, although the magnitude of the force, so the size of the force, would affect the rate. If we had a bigger force, we have faster movement and greater rate.
So you were saying that this is how the other classes wanted it, that there was like an issue with it because you could be lacking something.
Actually, the TAs said that Dr. Eder and Dr. Schlater taught it in 2 different ways, and that Dr. Eder's involved comparing something to 0. Dr. Eder says that's not what she taught. So the TAs did not say that you guys were confused, but since I saw that this back and forth, I knew I had taught you guys differently, so I figured I'd show you this as well.
Well, I didn't know like what you had said that it could be a little bit confusing just because we might not know chunk of it. What chunk of it we be missing?
So I don't think you're actually really missing anything. I think basically the way I showed you to do it is kind of solving backwards from like this step. And the reason I did that is because this one requires you to know the direction of the chemical driving force, which you won't always know. You'll often only know these 2 values. So then you wouldn't really be able to tell same direction versus opposite direction, which is why I don't like this chart.
So you can follow this as long as you have the CDF, but if you don't have the CDF, you have to do it backwards. Like start.
Yeah, basically, if you don't have the CDF, this becomes more difficult because if you don't know the CDF, what does following the CDF mean?
Right.
Right.
Okay.
Which is why I don't like
And
it.
can we have time to go over like one more of these the way that you initially explained it to us?
Sure, and I have a bunch of problems here on the worksheet that you can practice with. So maybe we'll do it that way.
Okay.
So it's problems 6 through 10. And when I told you that you should remember, like if you really struggle with this, that you could memorize specific situations, I outlined them all in this worksheet, the ones that you will expect to see for neurons, which is a lot of them. So I don't recommend memorizing them. It's easier to just understand the concepts, but if you practice those specific problems, that's what you'll see again in unit 2. Any overall questions either about the test or specific sections of lecture that you'd like to go back to before we break out and do some of these kind of practice problems to jog your memory?
Well, I just got my textbook yesterday.
I'm glad I came.
Yeah.
Sorry to hear that.
Are there any like chapters or sections that you really would want to highlight, do you think?
I would stick to whatever we talked about in lecture is what you should be paying attention to most
Don't worry
from,
about like
from the
learning new
textbook.
material in the text.
No, like there's a chunk of chapter 2, like a lot of it is about organelles, but we honestly hope you have learned that in your previous courses. So there was a little bit of that in the mastering A&P homework stuff. But since we didn't talk about it in class, it's not going to be an emphasis on the exam, basically. Yeah, does that help?
Yeah.
So, and you can consult those outlines as well. I think I made some notes in the module. I think I told you in some places like skip this section or don't worry about this as well. I am personally a big proponent of textbook reading just because I like reading stuff that makes sense to me. But we do try to go over everything we need to know. Especially, yeah, no, I don't recommend you try to read the whole textbook first. Yeah, and I did post this on the right way, so you can pull it up on your computer as well.
We got an extra lucky winner.
Thank you.
No problem.
We're gonna work on these, and as they bring up like questions and things, let me know and we'll go over those sections.
An
But
extra lucky winner.
if you want to start with practicing this stuff for the ECDF, that's on the back, so it's questions like 6 through 11. Figures and then you understand what's going on with figures might help. You're trying to go through stuff fast. A lot of it will be small, but the lesson will just like kind of go straight through the stuff that's not that kind of area.
But like memorizing.
Yeah,
Very specific kinds of like.
yeah, I would focus on anything that was like confusing for you in lecture. So that I can do that section. Yeah.
Are you gonna post the key for this?
Yeah, after class. Or a link. But see, I created a FI module. So you can see that on the left.
They're all. I have a quick question with the quizzes.
Yeah, so it's-
So are you not able to see?
yeah, let's see, we have a couple people. Oh, okay, so I'm gonna read this.
Oh, okay.
It doesn't remember what they went out.
It says it's been
Okay, great. So no, that is the base. That's plenty to study for. Glad I thought about that with your schedule. You find out.
Study guide or something like that, that you can't get.
I have never been to SI, so I don't know very much about what happens there unless the TA email me telling me something. Is that true? Does SI distribute a study guide for this?
It's like a worksheet.
Okay, so it's just these worksheets, but
Oh, okay.
you can email the TAs about that as well. These are very complex information. I'll make sure to post that as well. All right, I'm staring at this chart, thinking about it more. So in the situation where you don't have the chemical driving force, I think you would just do this bottom part, and then it kind of doesn't matter because it's in the media versus the direction. So you might pop back up and end there and get the right answer without knowing that there's a direction.
I know, like. I know.
You can keep it, it's just for studying, kind of guided practice, and I'll post a key. Yeah, I'll post a key. I'll just pop up to my office and do it after class. I figured, there was no point in sitting in the review section and looking at the key. Yeah, I could have now, let me see, I'll have to link. We've been talking for a while, so you guys came to class. That's the main point.
It's just, we have